Right, so today we're looking at something called double angle formulae, and this is about thinking about the same angle being there twice. So I've cleaned out all the take ones. So if you were looking in your formula booklet, you would see that and that and that, and then that would be the other way up, wouldn't it? And you would see that and minus there, and then the plus. That wouldn't be the other way up, would it? Because these are all, what would be? That would be the plus there. So anyway, we're going to ignore those red ones, even though I've just put them in there. But I put them in because when you're looking at the formula booklet, you've got to be able to weed that out. So what this is all talking about is if you had a double angle, so if instead of A plus B it was A plus A, so it's just the same angle twice, you could call it sine of 2A, couldn't you? And then you could say that that was going to be identical to, well, if these were both the same, that would be A and that would be A as well, wouldn't it? So sine A cos A, well, that's going to be the same as cos A sine A. So we can say that we've not got one of them, but 2 sine A cos A. I'm going through this gradually because you don't get this in the formula booklet. You've got to create this from that when you see some of these double angles popping along. Now the next one is going to be for cos 2A. And if we do that, it's going to be cos A cos A. Well, cos A cos A would be cos squared A. And then we're going to be taking away, if that was an A as well, sine A times sine A will be sine squared A. So that's one identity you can get from it. But you may notice that this looks rather like one of the very first identities you learned, and one that comes up again and again and again, that lots of them sort of all come from, and that is this fact that if you've got sine squared theta plus cos squared theta, that equals 1. And you can rearrange that so that you can say that cos squared theta equals 1 take sine squared theta. And if you were to do that, you could have a little look at this and replace the cos squared theta with 1 take sine squared theta, which means that cos 2A is not only identical to that, it's also going to be identical to 1 take, well, you've got 1 sine squared theta there and another negative sine squared theta there, so 1 take 2 sine squared A. Now that's not the only thing we could do with that. We could also, if I just pull this down here, we could rearrange it so that we've got the sine squared theta is equal to 1 take cos squared theta. And instead of substituting the 1 minus sine squared theta in for the cos squared, we could put the 1 minus cos squared theta in for the sine squared. Now you've got to think quite carefully about that, because what's going to happen then, I'm going to be taking this in a bracket, so I'll take 1, but then what happens when I take a negative? I add, and what all of that means is I end up with cos squared theta plus another 1, so as we're in A's here, that'll give me 2 cos squared A, and we were taking 1 that time. So I'm going to put a little bit of a bubble around here so that we think all of these are cos, not cos 2's, cos 2A's. And all of those can come up and be relevant. And then finally we've got tan. So we've got tan 2A, and that's identical to, well, when we're adding, we're still adding on the top, so that's going to give us 2 tan A on the top, but it switches here, doesn't it? Plus goes to minus, so then it's 1 take tan A times tan A will be tan squared A. And there are various problems we can solve using that, which is where we're going next. Right, here's 3 different problems that we could use the double angle formulae to simplify, in effect, everything that we've got. So we want to have, instead of 2 trigonometric ratios, just the one. 2 different ones there, 2 different ones there. We're going to end up with the one. So pause the video, have a little look back at what I've just shown you, and see if you can find which one's going to be appropriate to use each time. So the one that we had up there was that cos 2a is identical to cos squared a take sine squared a. So all I need to do is say that if I've got cos squared 50 take sine squared 50, because that angle's the same both times, that means I would have cos of 2 50s, which is 100. So it's cos 100. The second one here, we're going to be using the tan. So we know that tan 2a is identical to 2 tan a over 1 take tan squared a. So all we're saying here is that if we've got 2 tan pi over 6 all over 1 take tan squared pi over 6, that's going to be the same as tan of double the angle. Well, the angle here is pi over 6, so double that would be pi divided by half the number, 3. So tan pi over 3. There we go. Right, and the last one, not necessarily quite so obvious, this one. And generally the key to making sense of this here is to sort out, whenever you've got a sec, a cosec or a cot, is to put it into the function that you do understand. So well, I know that 1 over, I know that sec 70 is equal to 1 over cos 70. Well, that would mean that 1 over sec 70 must equal cos 70, mustn't it? Because it's the reciprocal. So we're just turning it upside down. So that means that we can say that that is going to be identical to 4 sin 70 times cos 70. And now, if you have a look back at your double angle formulae, well, we've used a cos one, we've used a tan one. If you look at the sine one, we know that sine 2a is identical to 2 sine a cos a. So all we've got is we've got double the amount of it. So we will have 4 sine 70 cos 70. It's going to be identical. It's going to be twice the amount. So if I had 4 sine a cos a, that would be the same as 2 sine 2a, wouldn't it? So if I times, I'm going to have 2, and then it'll be sine 2a, but my a in this case is 70, so 2 sine 140. Alright, here's a sneaky little problem. So write this one down, have a little look at it, and the first place you want to look is where you've got the double angle, the 2 theta. So first of all, I'm going to rearrange it to make cos 2 theta the subject of this. So if I add 4 cos 2 theta to both sides and I take the y, I get that. Then if I divide by 4, I get cos 2 theta equals 3 take y over 4. Now I've got to eliminate the angle and express y in terms of x. So this is in sine over here, and I've got a cos 2 theta over here. Now what do I know about cos 2 theta? I know that cos 2a is identical to 1 take 2 sine squared a. So I'm going to say, right, this, I'm going to do this for both things. So I'm going to say that I know cos 2a is that, and I'm going to make that equal to this over here. That's been squared. So we need to get what we need to know what our sine is as well. So if I rearrange this, we can get that sine theta is equal to x over 3. So now that I know that, I can say that I know that this cos 2 theta, which is 3 minus y, is going to be equal to 1 take 2 of that squared, which is x over 3, if you follow me. So one last time, I've got my cos, I think that is my 3 take y over 4, and that is equal to 1 take 2 times sine theta squared, which is x over 3. So times x over 3 squared. So here's my equation. I've eliminated the angle, and all I need to do is put it y in terms of x means make y the subject of the formula. So if we multiply everything by 4, we get 3 take y equals 4 take 8. Let's square that, x squared over 9. And we've got minus y, haven't we? So if we add y to both sides, and then I'm switching it from left to right in the same go, so maybe I shouldn't do that. Maybe I should just leave it as 3 take 4 is negative 1, and I'll have 8 x squared over 9 take 1 is equal to y. So therefore y equals 8 x squared over 9 take 1. And that's that one done. Not so nice, that one. Final example for today. Write this one down and give it a go. So I know sine 2x, it's quite nice when you get the sine ones rather than the cos ones, because you know that all you have to do is start with what your sine 2x is going to be. So that is 2 sine x cos x, isn't it? And we know what cos x is, but we don't know what sine x is yet. So we do need to know what sine x is. So in order to do that, we need to use the good old fact that we know that cos squared x plus sine squared x is equal to 1. And therefore, if we want to know what sine x is, if I say sine squared x is going to be 1 take cos x squared, so cos x is 3/4, so if we square that, that means that sine x is going to be the square root of 1 take 3 squared is 9 over 4 squared is 16. That is going to be 16 take 9 is 7, isn't it? So the square root of plus or minus the square root of root 7 over 16, which we can say is plus or minus root 7 over 4, can't we? and we need to know whether or not it's plus or minus, don't we? So we know that our cos x is 3/4. So if cos x is 3/4, and we're between 180 and 360, and 3/4 is going to be about there. So we are looking at a positive value, aren't we? So we are looking at √7/4. Except, hang on, why am I doing the cos curve? This is when we've got sine x, isn't it? Sorry about that. We should be having between 180 and 360. That's negative, isn't it? So I just put a negative in there, and we can keep that between ourselves, can't we? Right, so we know that's what sine x is. So I know that sine 2x is going to equal 2 times negative √7/4 times cos x, which is 3/4, and we just need to put all of that together. The 2 will cancel there, so we will get negative 3√7/8. So that's part A. And then part B, tan 2x. Well, we know that tan 2x is identical to 2 tan x, and then it's 1 take tan squared x. Before we go any further, we need to know what the flip tan x is, and we are talking about sort of flipping, because we know that tan x, pop it up here, is always equal to sine x over cos x, isn't it? And we now know that, so we know that sine x is negative √7/4, and we're dividing that by cos x, which we know is 3/4. So that's going to be the same as negative 7/4 times 4/3. Oh, that's nice, they cancel. So tan x is √7/3. We now need to plug that into here. And we're going to get 2 √7/3 all over 1 take √7/3 squared, and you can pump that into the calculator, or we may as well keep going, mightn't we? We can say that that's going to be 2 √7/3 and divided by 1 take, what's that, √7 squared is 7/3 squared is 9, so that will be 2 √7/3 divided by 2/9. So then we can say that's going to be 2 √7/3 times 9/2. We can cancel there, we can cancel there, and we get 3 √7 as our final answer, except that I have just missed out somewhere in here on a negative, haven't I? Negative there divided by that, that would give me a negative as well. So that should be negative 2 root 7 over 3. Yes, there would be a negative in there, but that wouldn't matter because on squaring it, that would come out. So in the end, this should have been a negative. So sorry about that. That should be negative there. That should be negative there. That should be negative there. And there's our final answer. Right. That's all very nice. Now, time for a little bit of practice. Exercise 7C, page 175. Questions 1, 6, 14, 15, 16, 17, 18. Quite a few there. Do as many as you can until you're comfortable and confident with it. The more practice we do, the better ingrained it gets, doesn't it? And answers on page 394. Okay. See you tomorrow.